So now we get to the big real problems. These problems are basically gonna show us how we're gonna use what we've learned in real life examples. And this example comes from the medical system. So this is the time again to pause the video and read the example and try to at least set up the problem. So in this case, this is obviously this is in the service industry. We have a hospital, the ER room in a hospital, and we have patients entering the ER room to get some care. And then so the patients come in, and there's two alternative outcomes. Either a patient is seen by the doctor and they realize that the patient needs to be admitted to the hospital. And then there's the other alternative where the patient actually does not need to be admitted to the hospital and a simple prescription is written and the patient goes home. So they're telling us that 50 people arrive at the, so we have 55 people arriving in the ER room, and they're telling us 10% of them are admitted to the hospital. On average, 7 people are waiting to be registered. So we know that obviously when they come in, there's registration, and that registration takes 2 minutes. And so 7 people are going to be waiting to be registered. And then once they're registered, there's 34 people waiting to be seen by a doctor. So if a patient ends up being a prescription patient, so a patient that does not need to be admitted to the hospital, they will spend an average of 5 minutes. While for those that are going to be admitted to the hospital, they're going to be spending 30 minutes with the doctor. We're assuming that the process is stable, which basically means we could use Little's law. And we have the first question asks us, how long does a patient spend in the ER room? So the first thing we need to do is draw a process map. This is the most important thing. And here is the process map. So we have to basically absorb everything we just read and basically draw a process map based on what the question says. So we know that there is so again waiting is annotated with triangles. So triangles for waiting activities or waiting stages, and then the actual registration is a triangle and doctor visit is a triangle. Now, also before we go into the drawing of the process, we have to understand in this question, the flow units, at first, they are the same. Patients are entering the hospital, it doesn't matter. So a patient is before the checkup, we don't know which patient is a simple prescription patient and which one is a potential admit patient. So, but once this is identified, then the flow units are going to be, we're going to have 2 different flow units. Now, this is very important. This is quite different than the other questions we've seen before. So we have, first of all, there is the customers walking in. So maybe let's have it in red. So we have, or maybe yellow is better. So here is we have the buffer. So the patients, they enter, they're waiting to register, and they told us that there is 7 people waiting to be registered. And then after that, we go into the they go into the registration. So after the waiting, they get to register, and that will take 2 minutes. And so that's we have registration, and then we have another waiting. And again, we're just basically interpreting the question. That's all we're doing. We're just drawing what the question said. So we're drawing the process. So then we have another waiting station, and then this is the waiting to get seen by the doctor. And they told us that there is 34 patients in waiting, so they are in inventory. And then we go on to see the doctor, and here we get two different times. One time is for if a patient ends up being a simple prescription patient, and then we have if the patient turns out to be, and that turns out that that patient needs to be admitted to the hospital. Now we see 10% here and 90% here. Now this is so this is why we're showing 10%, 90%, because here the flow rate is gonna be specific. So we're gonna have a flow rate for potential admits and flow rate for simple prescription. So initially we had the flow rate of 55. So because that's what they told us there's 55 people arriving in the ER. So that's initially, but once we get to the doctor, we're gonna split into 10% potential admits. So that's gonna be 10% of that flow rate, and then the simple prescription are gonna be 90% of that flow rate. So so this is basically the process map. So what we want to do is the question asks us how long does a patient spend in the ER? So we're going to add all the different times throughout the station. So we're going to look at the time they are in buffer 1, the time they are in registration, how time they are in buffer 2, the time they spend with the doctor, and then we're going to use a weighted average to know, because we're going to have two different because we have two different flow units. So it's a stable system. A flow rate is 55. We'll convert it to hours. The flow rate for potential admits, we're multiplying 55 by 0.1 because we know there's 10%. So we're going to get 5.5 per hour. So again, we are going to have a flow rate for potential admits and a flow rate for prescription. So the flow rate for prescription is 55 times 0.9, and we're going to get 49.5. So we have two different flow rates, one for the potential admits and one for the prescription. So now we're basically going to be looking at all the different stages, and we're going to calculate the time for each stage. So we start with buffer 1. And we know at buffer 1 we have 7 patients in the inventory. R is 55 per hour. At this point, the flow unit is still patient. We didn't go specific into whether the patient is potential admit or simple prescription, because that hasn't been decided yet. So R is 55. And so to calculate the T is we're just going to go I over R, and it's going to give us 0.127 hours or 0.7.6 minutes. Now then we go on to registration. Now at registration, the time is already given to us, so it's 2 minutes. But here we're calculating the inventory because we will need it for later questions. So now in the next stage is we have buffer 2. So we have buffer 2 and doctor. We've already calculated buffer 1 and registration. So for buffer 2, we know what I is. So I is given to us 34, and we know the flow rate is still the same, 55. So the time would be just I over R, and we get 0.62 hours. Now we go into doctor time, and here the times again are given to us. For potential admits, T equals 30 minutes, and prescription patient, T equal to 5 minutes. So now we basically we have to basically add all the different times we have to add all the different times for potential admits, buffer 1, registration, buffer 2, and doctor. So we're just adding the numbers we've already calculated, and we're going to get 76.7 minutes. And for prescription patient, we're again adding all the different numbers, and 7.6 to 37.1 plus 5. Now notice the only difference between the potential admit and the prescription patient is the doctor time, because that's the only difference between them. And we're gonna get 55.7 minutes. So on average, because they're asking us they're asking us how long does a patient spend. So they're not talking about the potential admit or the prescription patient. So in general, the patient as a whole. So for this, we have to take 10%. So we're going to do like a weighing average, because we know 10% of the patients are going to be prescription patient. Sorry, 10% of the patients are going to be the potential admit patient. So we're going to multiply the time we got from potential admit by 0.1. And then we're going to add to that 90%, 0.9 times 51.7. Again, this is 0.1 and 0.9, not 10%. So we're multiplying by the ratio. And if we do this, we get 54.2, and that answers part A of the question. So an average patient spends 54.2 minutes. So at this, now the question, we're in part B, which asks, part B asks us how many patients are being examined by the doctors. Now, at this point, we have, at the doctor activity, we have to take into consideration that we have two different flow units, one which is potential admits. So we have the potential admits, and also we have the prescription, simple prescription admits. Each one of them is going to come at a different R. And remember, we said for potential admits, they're 10% of 55. So we multiply 0.1 by 55, we get 5.5. While for prescription, we get R 49.5, which is 90.9 times 55. So we know the time for each one of them. And what we want, we use the equation of I equals to RT. So basically so we know what R is, we know what T is, so we calculate I for the potential admits, which is going to be 2.75 patients, and for prescription is going to be 49.5 times 5 divided by 60, and that's going to be 4.125 patients. So the total inventory, the total number of patients at the doctor are going to be the sum of these two numbers, and it's going to give us 6.865. So the last part of the question asks us how many patients are in the ER. So basically at this, we're just going to look at all the different stages and sum all the different inventories. So we know that there's inventory in buffer 1 is I7, so that's it. And for registration, we've calculated that previously, 1.83. And we know for buffer 2, it's 34. For the doctor visit, we've just calculated that sum in the previous slides. So when we sum all this, we're going to get 49.695 patients. So I remember all these numbers are average numbers. So that basically concludes this question, which is a very interesting question. So we've seen a real life scenario of probably some of you have experienced going into ER and seen this sort of process where you have to register, wait to see the doctor and all that, all these different steps. So we see right here is basically the implementation of Little Law in a real life example. So let's move on to the next question. So for example number 8, we're adding, it's basically the basic example for number 8 is 7, so we're continuing from example 7, but we're adding a triage nurse. So there's a nurse that is the nurse, and the nurse will decide who will be the simple prescription and who would be the potential admits to the hospital. So our process is going to change a little bit. So we are adding a triage nurse here. And then we have two different waiting scenarios, one for potential admits and one for the simple prescription. And then the doctor sees the potential admits, knowing that they are potential admits, and then the doctor sees the simple prescription, knowing that they are simple prescriptions. So the process map is going to change a little bit. But the overall procedure, we're still looking at stages and we're calculating the inventory or time for each stage depending on what the question is asking. So how many patients will be in the ER? So they're asking for inventory. So again, we're doing the same thing as we've done in the previous question. We're going to be looking at the inventory in each station, in each stage. So in buffer, registration, buffer 2, triage nurse, buffer 3, buffer 4, potential, and the doctor visits, and we add them all up and we get an overall number for the inventory. Now we have to remember that the potential flow rate for potential admits is going to be 10% of the overall flow rate, while for prescription is going to be 90% of the overall flow rate. Throughput is we're gonna convert the throughput in terms of minutes because all our numbers are gonna be in minutes. So we're using the I equals RT formula to get the inventory. So we sum all the inventories. So we have 20 patients in buffer 1, so they're giving us the inventory here. Registration, they're giving us the rate and the time, so we use that equation to calculate the inventory. Buffer 2, we know there's 5 people. The triage nurse takes 1 minute, so we convert that again to an inventory by multiplying it by the rate. And buffer 3, we got a number here. The potential admits, we know it's 30 minutes. So we 30 times 0.1967 times 0.1 because we want to rate it for the because it's 10% for potential admits. Buffer 4, there's 15 people. Simple prescription, again we have the time and we have to convert the time into an inventory, and then we add all of them up and we get 50.627, the total inventory. Now we're going to assume, we're assuming again 90% of all patients are simple prescription. How long does a patient spend in the ER? So there's a shortcut to answering this question. So instead of going in every stage and calculating the time and just adding, we could just look at the overall system, and we know we just calculated the overall inventory, which is I that we calculated in part A, and we know the flow rate coming in and leaving the overall system, the whole process, all the processes is 55, so sorry, 50.627, sorry, 0.9167 because we converted it to minutes, and we're dividing by what we just calculated in part A, which is 50.627, and we should get 55.323 minutes. Now, if you were to calculate the time for each station, and so we calculate the T's and we add them all up, and we take into account the weights that 90% of our patients here are going to be simple prescription and 10% potential admits, you will get the same answer. Now, part C of the question is asking us how long would a potential admit spend in the ER. Now, what we're going to do is we're going to add up all the different stations or stages that the potential admits will go through. So the potential admit will go through buffer 1, registration, buffer 2, triage nurse, but obviously the potential admit will not go through the simple prescription path. He or she will go through the potential admit path. So we just add all these up, the times in all these stages, and this is actually in Excel. This shows you the times, and we add all these times, and it's going to give us 71.18 minutes. This is the answer. And how long a patient who has a potential admit spent in the ER.